Okay, why don't we start? And then, we'll see how things progress during the morning. So, hello, my name is Sara Bonella. I am the Deputy Director of CECAM, which is the European Center for Atomistic and Molecular Simulations. And it is my pleasure to welcome you all to this webinar, which is hosted in collaboration with the MultiXscale Center of Excellence for Computing Application project funded by EuroHPC. So this seminar is part of a continued commitment from CECAM in supporting and disseminating activities related to software development efforts in our community. This started a few years ago when CECAM was the coordinating institute for one of the Centers of Excellence for Computing Application called ECAM, and it has continued with a series of webinars called The Importance of Being HPC Earnest, in which we invited representatives from many software development and deployment efforts across the world to share their experiences with us. And it's now continuing with the newest generations of COEs. We had a nice seminar in collaboration with the T-Rex Center of Excellence for Quantum Monte Carlo methods. And today it's a pleasure to focus on multiscale simulation approaches. So you can find all these previous installments of this webinar series on the CECAM website or on the CECAM video archive that is called LUMOS. We will probably hear a bit about that at some point during this webinar, and if not, we'll type some info on the chat so that you can find it. This takes me to the first comment that I wanted to make. The webinar is being recorded for our archiving purposes, and I just feel that it's correct to inform any participants and the panelists of this. Here are also a few instructions for those of you who have joined us and would like to ask questions. You can only do that using the Q&A Zoom tool. These questions will be read by our moderator and relayed to the speakers. You can also monitor communications from us from the Zoom chat, but you cannot use it. The chat use has been disabled for participants. We would also like to inform you that MultiXscale has asked us, and we're happy to accept this request, to propose a short survey. It's very, very short, so not a lot of time invested in filling it, to help them track statistics for participation to this meeting, and this will be shared with you at the end of today's webinar. So that's all I had to say. It's my great pleasure to leave the stage now to Matej Praprotnik for the NIC Institute in Ljubljana, who is the coordinator of the MultiXscale project. Matej, the stage is yours.
Okay, thank you, Sara, for this nice introduction. I'm Matej Praprotnik from Ljubljana. I'm the project coordinator of MultiXscale, the EuroHPC Center of Excellence. And I will just start with a short presentation of the center. So what is MultiXscale? So basically, this is the goal of our Center of Excellence is to develop multiscale software for efficient simulation, multiscale simulation using exascale supercomputing power that EuroHPC offers us. And it's a collaboration, as already Sara mentioned, between CECAM community and EESSI members, which will be introduced later on in the seminar. And we are focusing really to provide user-friendly, easy installable software to solve social challenges using supercomputer. And in particular, in our case, we are focusing on biomolecular applications using ultrasound, then battery applications where we are focusing mainly on supercapacitor systems for sustainable energy, and civil transport using helicopters, where we focus on turbulent simulation of rotors and their interaction with the flow. Now you might wonder that these are quite let's say different applications. What is common to all these applications? The common thing is that they represent complex systems, And these complex systems are inherently multiscale. So they involve, so all the physical properties are determined by the interplay of different length and time scales. And the most efficient, from theoretical point of view, way how to tackle these problems and model them is to use multiscale modeling and simulation approaches, where we combine different methods and various length and time scale and couple them together. Of course, if you want to then harness the power that supercomputers offer us, the theoretical, so the algorithms have to be then integrated into community software packages that allow us then to use this HPC supercomputing power at disposal. And basically, in our case, these open sources are basically ESPResSo and LAMMPS for particle-based simulation, MD, DPD, and similar. And then waLBerla for lattice-Boltzmann simulations, where we basically employ computational fluid dynamics approaches. And now the idea of these different computing software packages that have to be coupled together in order to provide a multiscale software stack. And that's actually the goal of our MultiXscale Center of Excellence, to provide the software, multiscale software, which is easily installable and user-friendly with the continuous integration and development support. And this is actually a software that is basically at disposal for all scientific and engineering community. In our particular case, we are focusing on the CECAM community, where we actually provide this software, and then this software can be then adapted to the needs of the different scientific groups. Basically, it releases them of the burden of all this installation and difficulties that you encounter as a scientist, where you want to install your software on your either local computing cluster or basically on different architectures, supercomputing architecture across the EuroHPC system, or even in a wider scale. So this is actually now the MultiXscale in the nutshell. So basically, the methods and algorithm, the multiscale methods, they come from the CECAM community. So these are various approaches that we were developing in the past, let's say, decades. And now, and the open simulation codes, also the community provide different open simulation codes. And now the idea of MultiXscale is to couple these codes into a common MultiXscale software stack. And then basically through this collaboration with EESSI, this software can then be automatically streamed on different EuroHPC machines, and then further used for solving different social problems, as I said, in our case, connected to these three scientific pillars. And in this way, of course, the availability of this tremendous availability of these HPC machines that EuroHPC provides can be then used really for really beneficial purposes to our society. So this is the agenda for today. The whole webinar will take approximately 3 hours. There will be a Q&A session involved, and maybe I should just mention before I go to agenda that this is basically the MultiXscale Center of Excellence involves 16 consortium partners all over Europe. There are the logos. I will not go into the separate organization now, but we can start with the introduction to EESSI, which stands for, it's so easy that I always have to think of what it stands for. It's basically European Environment for Scientific Software Installations. And the introduction will be actually given by Kenneth Hoste from Ghent University. So Kenneth, the floor is yours, and I will stop sharing my screen.
Okay. Thank you, Matej. All right, let's see if this works. My screen share should be up now. You should be seeing terminals now as well. Is that correct?
Text is a little bit small.
Yeah, I know. There's a reason for that. I'll have to keep it like this.
Okay.
All right. So I will quickly introduce you to, and Zoom is getting in the way here. Okay, to EESSI, the European Environment for Scientific Software Installations. This is the technical aspect, let's say, of the MultiXscale Center of Excellence. All right. So as Matej already briefly mentioned during the introduction, there's a bunch of challenges that we see today for scientific researchers when they need to do computational science in general. The first one that I'm sure many people have noticed is that the diversity in system architectures especially in the EuroHPC systems is growing quickly. Two very clear examples of that are Deucalion in Portugal, which has an ARM partition, and the upcoming Jupiter in Germany, the big exascale system, which will be fully ARM based. So that's a very different system architecture, and that will come with some pains in terms of getting your software running there and getting it to run well. We also see more and more software being used by researchers, more different tools that we didn't see before. Some of them with very deep dependency stacks, and the AI boom is certainly a part of why that is a problem today. On the flip side, we see a lack of sufficient manpower in the support teams of the big systems, even for the big systems. So they cannot really help everyone, and the researchers to some extent have to help themselves and figure things out by themselves. What would be really helpful if there would be a uniform software environment across systems, for example, in the EuroHPC ecosystem. But today that's not really there, and that's one of the things we're hoping to help with. And there's also currently no central service for continuous integration, continuous deployment of the software that people are developing. But that would also be very helpful, especially to researchers who develop their own tools. So we want to tackle these challenges with EESSI, with the European Environment for Scientific Software Installations. And the key thing we bring forward here is like a dream or an idea where we say, what if you actually don't have to install the software that you need anymore, regardless of whether you're using a laptop, an HPC cluster, or working in the cloud. And what if you could do that without compromising on performance, so without sacrificing performance by doing that? This is essentially what EESSI enables. So EESSI is the European Environment for Scientific Software Installations. Very simply put, what it is a shared repository of scientific software installations, which are optimized for particular types of hardware, so particular types of CPUs. What we want to do here is build a shared software stack, and by doing so and collaborating with many partners, we avoid a lot of duplicate work. By doing that, we also provide a uniform way of providing software to users. So regardless of the system you are working on, you'll essentially get access to the same software installations, and you can use the same kind of workflow as you're used to from other systems or even from your laptop. We want to set this up so it works on any system, any Linux system, whether that's a laptop, an HPC cluster, or whether you're working with virtual machines in the cloud. That shouldn't matter. It should look and feel the same way. It should work in the same way as well. And there's a very strong focus on performance when doing this. We don't want to sacrifice performance in any way, as is often done with other mechanisms of taking the software with you, for example. We automate as much as we can, we test as much as we can, and we're very keen on collaborating with others to make this work. So what EESSI essentially is a uniform software environment, in particular for the EuroHPC systems, but also beyond that. So in the scope of multiscale, as Matej already mentioned, we're mostly focusing on a couple of scientific applications. like waLBerla, ESPResSo, and LAMMPS. But we're already pulling in additional tools as well as the scientific side of the multiscale project figures out how to couple these methods, how to implement various methods to do these multiscale simulations. So it's already expanding a bit into other tools as well. So we're quickly going to dozens of applications that will actually be needed to do the research. If all of these applications are installed in EESSI, and that's in some sense a one-time effort, and if EESSI is available on all the EuroHPC systems, which is an explicit goal we have, then we reduce the burden for scientists quite a lot. So they essentially get the same software environment on each of these systems, and even beyond that, like on your own laptop or in the cloud. So the end user experience of this is may feel a bit weird initially and may feel a bit like magic, and that's a good thing. And the best way to experience it or to fully understand what we're doing is to really see it in action. So I have 2 slides here that basically show you the basics. If EESSI is available on a system, the first step is to initialize the EESSI environment by sourcing a script that we provide. That will detect what type of system you're running on, what type of CPU is available, and if there is an accelerator, a GPU available. If that's the case, it sets up the environment for you, and then you can start loading modules and running the software. And I have a very concrete example of this prepared. So I want to run ESPResSo on the Vega EuroHPC system on a GPU node that is available there. I want to set up my software environment and then run a small example of that. So let me do that hands-on. Let me switch to a terminal here. I have 2 terminals side by side. There's a reason for that. On the left, there's the Vega system. On the right, there's the Deucalion system in Portugal. So on Vega, I will be using a GPU node, an NVIDIA A100 GPU node. So let me set up that session. And the Vega people were kind enough to provide a small reservation for me, so that should get started really quickly. And if I check here, I'm on a GPU node, which has an A100 GPU available. All right, the first step here is to set up the EESSI environment. So I sourced that init script that is also mentioned in the slides. And you'll see 2 things here. Well, you see a bunch of things, a bunch of output. But the important thing here is that it detects what type of CPU we're running on. So it detects an AMD Zen 2 or an AMD Rome CPU. And it also figured out that we have an accelerator available, an NVIDIA A100 GPU, which supports CUDA compute capability 8.0. So that's essentially what this line means. Based on that, it will make some changes in our environment. It will essentially make this location here, which is a directory that has modules available. It will add this to the module path, and that means we can start loading modules now. So if we now do a module avail and we look for ESPResSo, we should see that ESPResSo is available through EESSI here. This is the GPU capable installation of ESPResSo. There's a couple of other versions as well. These are CPU only. It also finds Quantum ESPResSo, which is another software package. And in this case, we actually still see the local Vega software stack, which has Quantum ESPResSo, but not ESPResSo. So if we would want to run ESPResSo on Vega, we would either have to install it ourselves or submit a request to the Vega support team to install it for us. Through EESSI, we don't have to do that, and we can actually proceed and just go ahead and run ESPResSo simulations. All right, so the EESSI environment set up, I can now load a bunch of modules for ESPResSo, but also for some other small Python tools, which I'll need here to run a Python script. So when I run a module load command, if I run module list afterwards, you'll see this is a whole bunch of software packages that are available, ESPResSo itself, but also all the dependencies of ESPResSo and the dependencies of all these other tools as well. All of this is coming from EESSI. And what's actually going on in the background here, and I'll get back to that a little bit later as well. Whenever we're trying to access software or run software, that software will be downloaded on demand. So those particular binaries and those files that consist or are part of that software, those files will be automatically downloaded and cached here locally on this node. So even though we provide software, hundreds of gigabytes worth of software already, only small bits of that are downloaded as they are needed. And that makes this a really powerful system. So this sets up our environment for running ESPResSo. And now I can run a small example here which was provided by Jean-Noël, who's a partner in the MultiXscale project. He's way better than me at explaining what this means scientifically, but this is essentially using ESPResSo to do a small scale simulation and then provide a plot that essentially shows the results of that. So this essentially shows that it works, and it was really quick because it was running on GPU. Now, this whole procedure of sourcing the init script, loading the modules, and then running the script, what EESSI really enables is that you use the exact same workflow also on other systems. So even if that system is totally different, in the case of the Deucalion, for example, here we are running on the A64 FX partition, so the ARM partition of the Deucalion. We can actually use the exact same workflow. There's one exception here. Currently, on the Deucalion, EESSI is not available system-wide yet. So if you try to access it, it won't work. There's a small trick for that. There's tools that you can use even if the EESSI environment is not available system-wide yet. There's a tool called CFMFS-exec, which you can tell it, please make the EESSI repository available. And in this case, drop me in an interactive shell in which this is available. Now, this is not ideal. This will be a bit slow because things will be downloaded on demand here as this goes. And this is certainly for running multi-node simulations, this is not ideal. But the Deucalion team is actively looking into making EESSI available system-wide as well. So we can already play with it for small scale stuff and to show you that it works. But it's not ideal. So you'll see lots of delays here when you start doing this. So it's now essentially setting things up for us. So we're dropped in an environment where EESSI is available. So if we do the ls again, you'll see that now we can actually access this repository. And from this point forward, we can run the same procedure. We can source the init script, which will again detect what type of CPU we're on. In this case, it says it's running on a generic ARM partition, which is not true. It's an A64 FX partition, but we're still working on the A64 support in EESSI. But it will give you something that runs at least. And it couldn't find any accelerators. There's no GPUs in the ARM partition of Deucalion. Once we've set up the EESSI environment, we again have ESPResSo available from EESSI. Of course, these are only the CPU versions. There's no GPU support here, so we don't expose that module on a non-GPU system. And here it's essentially the same mechanism. We load the modules that we need to run the Python script. In this case, we load the CPU-only version of ESPResSo. And again, you see here that this is a bit unresponsive. That's because we're using that workaround through CFMFS-exec to access the EESSI repository. So this is definitely not ideal, but it will work if you're a bit patient. All right, so that sets up the environment. Again, output of module list will show that lots of modules were loaded, essentially the same modules as we had on Vega, so the same software environment. And here we can run that same script. In this case, I will do a 4-core MPI run here, which will eventually also show this graph. So it will be a bit slower because it doesn't have a GPU, and it's actually using non-optimized binaries on A64FX, which is not ideal, but it does work. So eventually, after a couple of seconds, it should complete and show us that same type of plot. So you can see how EESSI enables you to use the same kind of workflow across very different systems, and you basically don't have to worry anymore about the details underneath of how things work. So that was the quick demo. All right. So you can essentially, if you have access to Vega, especially because their EESSI is available system-wide already, you can use the same procedure. And you can use ESPResSo or any of the other software packages we currently have available in there. And the key thing here is you get the same software environment across potentially very different systems. So how does this actually work? So EESSI is constructed in a very particular way to enable this. So it's essentially a 3-layered design where we have a file system layer, a compatibility layer, and a software layer. The file system layer is essentially a certain VMFS repository, which enables this kind of streaming software. So you can see what software is available. You can set up your environment to start using it. And only when you're actually running particular binaries, those binaries will be downloaded on demand if they're not available locally yet. So it's only downloading very tiny parts of the full software stack we provide. as they are needed. So things are streamed in on demand, essentially. The compatibility layer in the middle is a middle layer that we build ourselves to get control over which libraries are being used for the software that we provide. And this is necessary to make it independent of the host operating system. So whether you're on a system that runs, let's say, a CentOS or a Red Hat-based version of Linux, or something that's Ubuntu or Debian-based, which are very different Linux distributions, we don't really care too much, because we will not be using the libraries provided by the host operating system. We will use the ones provided by this middle layer, by this compatibility layer. And this is essentially the same approach that is used in containers. We call this containers, but without the containing, because you don't need a container runtime, and you don't need to pull tricks to get it to work well with MPI, so with multi-node runs, or with GPU and so on. So you actually run into a lot less issues than the ones you see with containers. And then the top layer, the software layer, this is where we provide the optimized applications and all of their dependencies. So this is where ESPResSo, LAMMPS, and waLBerla are installed. And they're not installed once, they're installed multiple times for different types of CPUs and even different generations of CPUs. So we'll have a separate installation, a separate software stack in the software layer for Jupyter, for example, and for the ARM partition of Deucalion, and for the CPU partition of Vega, and so on. So these will be specifically optimized for those types of CPUs. And what else in the software layer is an initialization script, which you saw. It auto detects what type of CPU, what type of GPU is available on the system. And based on that, it sets up the environment for us. So how do you get access to EESSI? Well, EESSI is publicly accessible and for free. You don't have to register. You don't have to tell us you're using it. You can just follow our documentation to get access to it and start using it, whether that's on an HPC cluster or on your laptop, or whether you're playing with virtual machines in the cloud. It should be compatible with any of those systems. You can also use it on a Windows laptop through the Windows subsystem for Linux feature that Windows has. And on macOS, there's a Lima tool that you can use to spin up a small Linux virtual machine and then access EESSI through there. So it essentially works on any type of platform that we see being used by researchers. There's a recommended way to get access to EESSI. That's through what we call a system-wide native installation. That essentially means you install the CERN-VMFS tool or service, you configure it to know about the EESSI repositories, and then that's the best way to get access to it. That's how you get the best user experience. That's the situation currently on Vega. That's not the situation yet on Deucalion. That's why you saw those delays in getting access to the software. The downside of this is that this has to be done by system administrator. So you need administrator access to be able to install CERN-VMFS and configure it. If you don't have that access, you'll have to ask your support team to make EESSI available for you, or use one of the alternate ways of accessing EESSI. If people are interested in doing a system-wide native installation, and especially if you're new to CERN-VMFS, we did a tutorial end of last year that explains all the best practices for setting things up. There's also other ways of accessing EESSI, like the one I was using on Deucalion through CVMFS exec. Now, all of these come with some caveats. The user experience here is a bit less good. And depending on the type of work you're doing, so if you want to do multi-node runs, for example, this gets tricky pretty fast because you have to pull some tricks to make things work. On Deucalion with CVMFS exec, we've been able to do multi-node runs as well, but it took some additional scripting work to actually make that work. We have a blog post on that if you're interested. So there are other ways if you don't have system admin access, or if you can't do a system-wide installation, but they're not ideal. So what do we support today in terms of system architectures? We have support for x86, so Intel and AMD CPUs, and also different generations of ARM CPUs. We're also already working on RISC-V. So RISC-V is another CPU architecture which is getting a lot of funding, especially in the European ecosystem, and where we may see capable systems coming up in the next couple of years. We're essentially already preparing the software stack so that the software is there by the time the systems will be capable enough to actually run serious stuff on them. We have support for A64FX already to some extent. Not all the software is installed yet for A64FX, but we're working on that. And very soon we'll start working on NVIDIA Grace as well. That's the CPUs that are that will be used in the biggest partition of the Jupyter system coming up in Germany. Essentially, this means that we support any type of CPU you will see in practice, whether it's also on a laptop or in the cloud or even on Raspberry Pi boards. You can use our software as well. We're also working on support for accelerators. So the support for NVIDIA GPUs is there, as you saw on Vega, with a select set of software. So that will be expanded over the next couple of weeks as well. And we're already looking into support for AMD GPUs, which is very relevant, of course, for Lumi, for example, as well. Support various interconnects like InfiniBand, OmniPath, so all of these things could work. And we have a way of also injecting a particular MPI library, which is optimized for your system. So that may be important, especially if you're doing very big runs, that may be relevant. The end goal here is to really support all of the system architectures that we see in the EuroHPC ecosystem. So all the EuroHPC JU systems, we definitely want to support all of the hardware essentially that we see in there. And we think that's very feasible as well. So where can you use EESSI already today? In the EuroHPC JU ecosystem, it's available out of the box, so through a native installation on both Vega and Carolina. We've tested it on other systems like Deucalion, Discoverer, and Meluxina as well through the CMFS exec tool, and it works there if you're a bit patient in terms of getting the software started. We know that both Meluxina and Deucalion are actively looking into a native installation. So the sysadmin teams there are figuring things out, how to properly set up certain VMFS. That is a bit of extra work on a large scale. It's not as simple as setting it up on a laptop, of course, but it is very doable, and they're figuring things out, how they need to do that. And also in Jülich, they have expressed significant interest to make EESSI available on Jupyter. And we hope that will happen very soon after the system is available. And we'll actually work together with the team in Jülich to make that work and make it work well. Beyond that, EESSI is already available on various other systems across Europe. And also actually beyond that, also in the US and Canada and other places, it's already available. We're slowly building up a list of systems that we know have EESSI available in our documentation. So you can check the link at the bottom of the slide here to see where it is already available. And if you know about a system where it does work, but is not listed there yet, please let us know and we'll add it to the list. In terms of software that we have available today in EESSI, it's already a broad selection of software. We have over 450 different software applications, tools, and libraries available. That includes the software that's relevant for the multiscale project, like ESPResSo, LAMMPS, waLBerla, and some adjacent tools, but also additional large software packages, and which are typically difficult to install yourself in an optimized way, like OpenFOAM, like ParaView, like Wharf, or Quantum ESPResSo, are also available today. So you can start playing with those straight away. The NVIDIA GPU optimized installations, that's a smaller set. So today that's mostly ESPResSo and LAMMPS, together with some small testing tools. But we're working on lots of other software, and of course, PyTorch and TensorFlow there are very much on our radar for the AI workloads. And a full up-to-date overview of what we have in terms of software is also available in the EESSI documentation. A little bit more on the support for NVIDIA GPUs. So that does work, as you saw on Vega. There's a small set of software available today that's included in EESSI, and we're expanding that. The availability of an NVIDIA GPU is auto-detected by the EESSI initialization scripts, as you saw on Vega. So it will know what type of, first of all, if there is a GPU available and which type of GPU is available. So that's good. But there are a couple of caveats here. So for this to actually work and work well, EESSI needs to know about the GPU drivers available on the system. And we have scripts and documentation on how that must be done, but this needs to be done by the system administrators themselves. So you cannot easily do that yourself, at least not in, let's say, the proper way. So this involves creating some symbolic links in a particular location that EESSI knows about, so it can find the necessary libraries. We have good documentation on that. There is actually a workaround through LD preload, so you can essentially preload the necessary libraries and then things will work. But LD preload comes with a lot of caveats and it's not ideal, especially not for, let's say, large production runs. We definitely don't recommend this. But if we just want to test things, like today on Deucalion, for example, on the GPU partition, you will be able to get things running through LD preloading the correct libraries. So again, this is something where you may need some help from your system administrators. On Vega, they've already done what's necessary to make it work out of the box. We're also working on support for AMD GPUs, so we hope to have some support for that by summer next year. And of course, this is all documented as well. Then going into CI/CD, the CI/CD aspect of EESSI a little bit. Now, Alan will discuss this in a bit more detail, but EESSI can not only be used on laptops and HPC clusters, you can also use it in continuous integration environments like GitHub Actions and GitLab CI, for example. What that essentially means is that you can get access to the same software stack that you will be using with production runs, but in the CI environment. So if you're building your own software like ESPResSo, for example, and you want to test it against the dependencies that it will actually be used with on the system, you can very easily do that through EESSI. And Alan will show how that works in a bit more in detail. And we're actually already seeing projects doing this. So PyMBE is already using EESSI in GitHub Actions to run the tests for their tool, for example. And also this is well documented. And then wrapping up, so a last bit here is our current main repository, software.eessi.io, which I was using in the demo, is intended for released software, so properly released software versions that have been vetted by the developers as being stable. So that's the only type of versions we install in there. But of course, software developers sometimes also want to test or want to run pre-release builds where they're still developing additional features or additional improvements to the software. They want to be able to easily run tests with those pre-release builds as well. This is also a use case we support, and especially in the MultiXscale project, we're actively helping out the scientific researchers who are developing their own tools. This is now, let's say, in a proof of concept stage. So we actually have a way of doing that and letting software developers both build and deploy pre-release builds of their software, and also deploy it through EESSI, but through a separate repository, which we call dev.eessi.io. So those builds will be shipped through the same kind of mechanism and will be accessible through CernVMFS, but they will not stay there over time. So this is like a temporary installation for testing purposes, and after a while, it will disappear again. Once the developers are done testing, or when additional changes have been made that essentially make the pre-release build no longer relevant. We currently don't have this documented yet. We're working on that, but that kind of service will be documented very soon and may be interesting to many people. All right, and to wrap up with, this was very quick on EESSI. So in about, let's say, half an hour, we have a more extensive webinar coming up really soon in a couple of weeks, together with the Epicure project in EuroHPC. So a full introduction to EESSI, which is essentially the same story, but a lot slower and with a lot more detail. We'll go through the whole story again. So that will be done on actually November. The date is wrong. It should be Friday, November 15th, I think. I'm sorry, I should have corrected the date. So we'll fix that in the slides that we make available. But it's a free webinar. It will be available online, and you will be able to register for it via the Epicure website. All right, and that wraps up my part of the webinar.
Okay, thank you, Kenneth. So let's move forward with the agenda. And the next one is the first scientific pillar of our MultiXscale consortium. So the talk and presentation will be given by Jean-Noël Grat from University of Stuttgart. And he will tell us about their efforts to improve the scalability of energy material simulation in ESPResSo. So please, Jean-Noël.